Hi, my name is Alan Guth, and I introduce the idea of cosmic inflation. This idea states that the universe explosively expanded space and time in a fraction of a second after the Big Bang. In the next fraction of the second, inflation expanded at a slower pace that continues to this day. However, the twist is that it is accelerating. In the next couple of minutes, I will guide you through the process of inflationary expansion. Here's some background knowledge. The Big Bang occurred 13.8 billion years ago, causing an explosive scaling up of space and time in less than a second. Unfortunately, we are not able to recreate nor go back in time to witness this. However, we are able to see the CMB, cosmic microwave background, which is like an opaque wall at the edge of the observable universe. The CMB radiation was released around 380,000 years after the Big Bang, which made the opaque wall into a more transparent state. It was at this state where scientists discovered that CMB had uniform temperatures all around. Puzzling, isn't it? This is where things get interesting. If everything about the inflationary expansion is true, this puts the Big Bang theory in a problematic state. The question arose from the previous findings of the CMB. How could points that are far away from each other, which had never had contact, have the same temperature? To explain this, astronomers use a spherical diagram called the observable universe. The observable universe is 90 billion light-years in diameter, which can be used by centering it on any observer. At the edge, we can see the CMB radiation line. According to astrophysicists, things that are within the Hubble volume are connected and influencing each other, even without having contact. The Big Bang theory has two major flaws it cannot explain: the smoothness and flatness of the universe. Smoothness is when everything in the universe is relatively uniform, and flatness is the shape or behavior of the universe. To determine flatness, astrophysicists use a parameter called omega, which is the universe's density to the critical value required to stop the expansion of space. If the omega value was less than 1, the universe would have been closed. If the omega value was more than 1, the universe would have been open. And when the omega value is exactly 1, you get our universe, a flat one. Here's how the inflation of the universe solves the smoothness and flatness problems. If you examined a soccer ball with a microscope, you might find imperfections that are as big in relation to the ball as mountains are on the surface of the earth. But if you imagine scaling the ball up to the size of the earth, any given point on the ball would appear relatively smooth. This is Alan Guth signing off.